Assalamualaikum and good afternoon everyone. In this video we will learn chapter 5, work, energy and power. Okay, for learning outcome 5.1a, define work done by a constant force. Okay, define work done by a constant force. Okay, work is defined as the scalar product between the force and displacement of a body. Okay, scalar product between force and displacement of a body. So this is the definition of work. So in formula, work equals to F dot S. It is dot product. Okay, F dot S. So it is equals to F cos theta. Okay, time S. It is also equals to Fs cos theta. Okay. So whenever you want to use this formula, work equals to F dot S. So the force, okay, the component of force should be the component which is parallel to the displacement. Okay, so you must multiply displacement S with component force which is parallel to the displacement S. Okay. So work is a scalar quantity and the SI unit is joule. Okay. It is easier to use joule, or the SI, the basic unit for the work is kilogram meter squared per second squared. Okay, so basically we use joule or the symbol J, capital letter J. Okay, work done on object is 0 when force is 0, or displacement as 0, or maybe we have value of F. Okay, whatever value of F, and we also have value of S, whatever value of S, but then the angle between force and displacement is 90 degree. That means force and displacement is perpendicular to each other. So the work done is 0. Okay, so sign convention for work done. Okay, so we have two sign convention for work done. Okay, positive and negative, and this sign convention does not represent the direction since work done is scalar quantity, so it has no direction. Okay, work done is positive if the work is done on the system. Okay, work is done on the system. For example, energy is transferred to the system. Okay, and work done is negative if work done by the system. Okay, for example, energy is transferred from the system. Alright. So angle theta for work done is positive, is less than 90 degree but greater or equals to 0 degree. Okay, for example, work done by the force F. Work done by force F. Okay, let's say we have this object. Okay, this object, okay, move to the right with displacement S. Okay, with displacement S, and then there is a pull force F here. Okay, so angle theta here. Okay, angle theta here should be less than 90 degree and greater than 0 degree. Okay, or equivalent to 0 degree. Okay, So we have positive work done. Okay, we have positive work done. Okay, if theta is 90 degree, work done is 0. Okay, when theta is 0 degree, work done is maximum. Okay, when theta is 0 degree, work done is maximum. That means the force F is parallel to displacement. It is like this. This is the object. This is the maybe floor. Okay, so F is parallel to the displacement as here. Okay, so this is example of theta equals to 0 degree. So for this case, work done is positive. Okay, work done is positive by the push force or pull force when it is same direction as the displacement S. Okay, how about the work done is negative? Angle theta is less than 180 degree or and greater than 90 degree. Okay, this one. Okay, example for this one is work done by the frictional force. Okay, work done by frictional force F. Okay, small letter F. Okay, let's say we have this object. Okay, we have this object on a rough surface. Okay, on rough surface. Okay, so this is the displacement S, displacement F, and then there is frictional force here, the frictional force. Okay, so the angle between friction and displacement is 180 degree. Okay, so work done by the frictional force is negative. So this is graph of force against displacement. Okay, the concept that you have to know for this one is, okay, so this is graph of force against displacement. Okay, the concept that you have to know is work done is equals to area under the graph of force against displacement. Okay, against displacement. Okay, but remember, force must be in unit Newton and the displacement S must be in unit meter. Okay, so if unit of force is given in kilonewton, you have to convert to Newton. You must convert to Newton. And if the unit for displacement in other unit of meter, for example, centimeter, is given in centimeter, so you must convert unit displacement to SI unit, which is meter. Okay. 5.2 Energy and conservation of energy. For learning outcome 5.2a, state the principle of conservation of energy. So principle of conservation of energy state that in an isolated system, the total energy of that system is constant. Okay, what is the meaning of isolated system or closed system? Okay, isolated system or closed system means that there is no external force. Okay, no external force. That means there is no air friction. Okay, so whenever we want to solve problem in chapter 5, we have to make an assumption that there is no air friction. Okay, no external force. So in mathematics, summation E is constant if summation F equals 0 or total energy initial equals to total energy final. Okay, So energy means we have to consider all kind of energy, included kinetic energy, potential energy, elastic potential energy, and energy loss due to friction. Okay, let us find out about the mechanical energy. Okay, mechanical energy is the sum of kinetic energy and potential energy in an object that is used to do work. Okay, kinetic energy is the energy of a body due to its motion. Okay, if the object moves, that means the object must have kinetic energy. Okay, so the formula for kinetic energy is K equals to half mv squared, where m is the mass of the object. Okay, and it is must be in unit kilogram. Okay, and v is the speed of the object, and the unit must be in meter per second. Okay, other than that, you have to convert. Okay, what about potential energy? We have two types of potential energy, which are gravitational potential energy and elastic potential energy. Okay, gravitational potential energy is defined as the energy stored in a body or system because of its position or height. Okay, an object at particular height h from ground must have gravitational potential energy. So formula for gravitational energy is U. Okay, the symbol of potential energy is U. U equals to mass m times acceleration due to gravity g times height h. U equals mgh. So mass must be in unit kilogram, and g is 9.81 meter per second squared, and height must be in unit meter. Other than that, you have to convert in SI units. Okay. What about elastic potential energy? Elastic potential energy is defined as the energy stored in elastic material as the result of their stretching or compressing. What is elastic material? Example of elastic material are rubber, spring, and maybe elastic string. So formula for elastic potential energy is US. Okay, so we want to differentiate elastic potential energy with gravitational potential energy. So we put S for elastic potential energy. US equals to half Fx, or it is also equals to US equals to half Kx squared, where F or Fs, okay, they are the same, okay, is the restoring force, and it must be in unit Newton, and X is the extension or compression of the spring. Okay, it must be in unit meter, and the K is the spring constant, and it must be in unit Newton per meter. Whenever we discuss about elastic potential energy, we can relate it with Hooke's law. Okay, what is Hooke's law? Hooke's law states the restoring force Fs is directly proportional to the amount of stretch or compression. Okay, extension or elongation of the spring. If, okay, there is condition here, if the limit of proportionality is not exceeded. Fs directly proportional to x. Okay, Fs directly proportional to negative x. Negative here, okay, negative here means the sign of Fs is always opposite direction of x. Okay, so in formula, Fs equals to negative kx. Okay, so in calculation, you don't have to put the negative sign. Okay, you also can just write Fs equals to kx for calculation. But for definition, you have to include the negative because the negative represent the direction of starting force F opposite direction to the direction of elongation or compression. So this is the graph of force. Okay, this is the graph of force against displacement x. Okay, like we discussed earlier. Okay, the area under the graph is equals to work done. Okay, area under the graph is equals to work done. Conservation of mechanical energy. In an isolated system, the total mechanical energy E of the system is constant. Mechanical energy consists of kinetic energy and potential energy. So, mechanical energy E is equals to kinetic energy, K, the symbol is K, and plus potential energy, the symbol is U. So, it is constant. In the image on the left, the total mechanical energy at any point is E equals to K plus U, where K is the kinetic energy and U is the potential energy. So formula for kinetic energy K is half mv squared, and the formula for potential energy U is mgh. If K1, U1, K2 and U2 are the kinetic and potential energy at two different locations, 1 and 2. So this is the location 1. This is the location 1 and then this is the location 2. Where location 1 is the initial position and location 2 is the final position respectively, then the conservation of mechanical energy leads to the following mathematical expression. Total energy initial equals to total energy final. Total energy initial equals to total energy final. Total energy initial consists of kinetic energy at initial position plus potential energy at initial position, and total energy at final position consists of kinetic energy at final position plus potential energy at final position. Formula for kinetic energy initial is half mu squared, where u is initial velocity and u is the potential energy. So the formula is mg h, and h here is the initial height. And the kinetic energy final is half mv squared, where v is the final velocity and the potential energy UF is mass times gravity times height at final position. Okay, so VI here we can replace with U, and VF here we can replace with V. Let us discuss about conservation of energy with dissipative forces. Dissipative forces such as friction, air resistance, push or pull by a person do not conserve mechanical energy. However, when these forces are taken into account, the total energy is still conserved, so it still obeys principle of conservation of energy. So total energy initial plus total energy loss equals to total energy final. So total energy initial consists of kinetic energy initial plus potential energy initial and then plus work done by the friction. It caused the energy loss, and energy final consists of kinetic energy final plus potential energy final, UF. So the formula is half mvi squared. So you may replace vi with u. So it becomes half mu squared plus mg height initial plus work done by the friction, okay, equals to half final velocity v squared. So you can replace vf with v and you can replace vi with u, okay, plus mg height final. In this case, work done by the friction is negative, okay, because work is done by the system to overcome the friction. Okay, thank you class.